Hi, today we're lucky to have Kai Liu from Georgetown University. Um, he's background's the following. He got his PhD in physics from Johns Hopkins in 1998 and did a postdoc at UC San Diego, and then went on to University of California, Davis in 2001. He became a professor there in 2008 and moved to Georgetown in 2018. He has many honors, of which the following. He's a fellow of the Institute of Physics in the UK, the American Physical Society in 2012, the IEEE in 2016, and the AAAS in 2019, amongst others. He's an expert in spintronics and nanomagnetism, and in particular, thinking about way to store information in topological widgets that you get with spin textures in small materials where they go around sort of in a circle that you can't just get rid of by knocking them with something. So I think it's a very interesting topic, particularly these days that the regular CMOS is really thinking about what goes next. So I look forward to your talk, and thanks very much for coming.
Thank you so much, Bob, for the introduction, and really an honor to be here. I wish I can plan the schedule better to visit you in person, but maybe leave that for next time. So today I will be sharing with you some of our recent work on Magneto Ionics and 3D nanowire networks. I will start with a brief introduction about Magneto Ionics, and mostly I will focus on using this handle to induce Dzerzhinsky-Maria interaction, and in turn to tune spin textures. And later on, I will discuss some other functionalities that we could control with this handle, namely exchange bias, and with some potential applications in 3D information storage. If there's time at the end, I will talk about something that's quite different from my conventional areas of research. I will discuss the use of metal foams for filtration. And as Bob has already mentioned, there has been tremendous interest in addressing the energy challenge in information and communications technology. It has been predicted that within this decade, the energy consumption in this sector will account for more than 20% of the world's total energy use. And in fact, today it's already more than 10%. And this has been reflected in the well-known coming end of the famous Moore's law. In fact, even though the number of transistors are still going up over time, but the clock speed has long saturated since earlier 2000. And we've seen pictures like this that you could fry an egg with the chips. And to address this, there have been numerous approaches in the field, particularly along the lines of trying to use electric field to control magnetism. And this bypasses the conventional charge current, which is somewhat inefficient. And here are just some examples of the seminal work in the magnetism field using electric field to manipulate magnetic semiconductors, to control anisotropy or Curie temperature in metallic ferromagnets or magnetic tunnel junctions or multiferroics. Usually the electronic effects are most prominent. The ionic effects are actually highlighted, particularly over the past 2 decades or so in memristors, where the electrical resistance depend on the prior history of the resistor. And this might be due to the conducting filament formation or breaking, or ion or vacancy migration. This has already found important applications in resistive random access memory, and people have shown the switching speed actually could be ultra fast, below 1 nanosecond. And there are also applications in using them for artificial neural networks. The magnetic version of ionic effects are best highlighted by this seminal work from Dominique Givaud's group And they show in 2007 that using electrolyte and the electric field, you will electrostatically drive a layer of charge on the exterior surface of the material. And this in turn induces another layer of the opposite charge along the interior surface. So right at this interface, you have basically a nanoscale electric double layer, nanoscale charge capacitor. So that modifies the carrier concentration and in turn the physical properties such as magnetic anisotropy. And this effect by nature, this is interfacial because of the electrostatic means. People later on have found out that there's also an electrochemical means where the charge can go into the material interior. There have been a number of excellent review articles on this topic, which I listed some representative ones here. What I will be talking about is the solid state version of Magneto Ionics, which is essentially atomic scale control of interfaces via ionic motion. This is done either electrostatically or electrochemically. And in essence, you are changing the interface to something completely different. People have found that the effect size can be very large. For example, in this seminal work by Jeff Beecher's group at MIT, Wei Gang Wang's group at Arizona, they've shown that in this cobalt gadolinium oxide system, the ion migration can induce very large magnetic anisotropy energy change, much larger than previous studies. We and other groups have shown that this effect can be realized in solid state systems well beyond the interface. And in fact, over the past several years, there have been many magnetic functionalities that have been shown that could be modulated by this handle, including magnetization, exchange interactions, ferromagnetic order, antiferromagnetism, and so on and so forth. And this can be done in an energy efficient way. And they are also compatible for 3D integration. To us, one particularly exciting angle is that this allows us to change the interface. So after you've made the material through this magneto ionic handle, you can transform the interface into something completely different. In essence, you are reconfiguring the system. And so that could be a interesting new degrees of freedom. So here is a couple of examples illustrating the magneto ionic control of ferromagnetism. This is perovskite lanthanum strontium cobaltite, about 36 nanometer epitaxially grown. If we put just a few nanometer gadolinium on top, gadolinium is able to suck oxygen all the way through this entire thickness of the cobaltite and turn that from magnetic perovskite into non-magnetic bromellite. Another example is on YBCO. This is example of now 100 nanometer thick YBCO. If we put a thin layer of a gadolinium on top of it, it is able to grab oxygen through this entire 100 nanometer. And this has led to very sensitive change on the superconducting transition temperature. There have been also complementary studies using ionic liquid gating. And this shows this electrochemical effect extend well beyond the interface. So in today's talk, I will mostly focus on DMI and the spin texture. As Bob already indicated, there has been tremendous interest on topological spin texture, such as magnetic skyrmions. And this is on the heel of last week's beautiful talk by Professor Kane on topology in momentum space. Here we're talking about topology in real space. And because of the topological protection, magnetic skyrmions have been envisioned as a very energy efficient information carrier. In fact, since its discovery in 2009, there have been studies, for example, this science paper showing the critical current density needed to drive magnetic skyrmions orders of magnitude smaller than the counterpart moving magnetic domain walls. A key enabling mechanism is this Jarzynski-Maria interaction. which is this anti-symmetric exchange. And so this leads to a preference for non-collinear spin configuration. And also because of the cross product, if we switch the adjacent spin, then the sign will change. So this lifts the degeneracy of left-handed versus right-handed rotation. And interfacial DMI was recognized by Albert Furr, Peter Levy, and others to account for this mechanism to drive the magnetic skyrmions. And traditionally, the interfacial DMI requires a ferromagnet next to a heavy metal and utilize the larger spin orbit coupling. And another characteristic is that once the material is made, this is basically set. You cannot really change it. And the interfacial DMI was observed in the earlier days by spin polarized STM. So what we set out to do is to see if we could use this magneto ionic handle to induce DMI after the system have been made. So we've done this in a controlled ultra-high vacuum system. And this also goes to address another challenge in magneto ionics, because the ionic migration usually happen underneath buried surfaces or interfaces. So it's actually challenging to directly observe the ionic migration and then try to correlate that with physical properties. So we want to do this in a controlled environment in ultra-high vacuum system, and we use chemi-sorbed light elements, oxygen or hydrogen, to explore the induced DMI. And in fact, we've done some other studies early on to study DMI in unconventional systems involving light element. The technique we will be using to study spin textures is a spin polarized low energy electron microscopy, which is an instrument stationed at the National Center for Electron Microscopy at Lawrence Berkeley National Lab. And it uses a spin-dependent electron reflectivity to give the magnetic contrast. And it can image spin texture with very high spatial resolution, approaching 10 nanometer. And also it can resolve the magnetization vector, so we can really directly visualize how the spins are configured in real space. And some of the previous work are discussed in this paper. So for our study, we first need to have a very clean background. It's kind of like when we do X-ray diffraction, we want to use this zero plate. So this background is this multilayer stack of nickel, cobalt, palladium, tungsten. And here palladium and tungsten have opposite DMI. So we can change the palladium thickness so that overall this stack is tuned very close to zero DMI point. The images here are the SPLIM images. The black and the gray area represent magnetization pointing out of the screen or into the screen. And then along the domain wall, the white arrows indicate the magnetization, the in-plane component of that magnetization. So when we start out with 2.1 monolayer of a palladium, we see all the magnetizations are pointing from black to gray. And this is illustrated in this schematic. So the adjacent spins are following this clockwise winding configuration. This is a right-handed chiral Neal wall. If we increase the palladium thickness to 2.9, we see the exact opposite. Now you see the arrows are all pointing from gray to black. And this corresponds to this counterclockwise winding. And in turn, this is the left-handed chiral Neal wall. And in between, at 2.46 monolayer, we see achiral Neal wall. So this gives us this clean background, and we're going to tune the system very close to this zero DMI point and see the effect of chemisorption. So we're going to start out slightly on the right-hand, on this side. So the system start out with the left-handed chiral Neal wall, and we'll see what happens as we introduce oxygen. And this is a video showing as we introduce oxygen, you will notice the contrast switches. Initially was white at the bottom, black on top. As we introduce oxygen, the contrast switches. And if we take a closer look at the different frames, so for example, when we only introduce 0.12 monolayer of oxygen, we see the arrows are all pointing from gray to black. This corresponds to left-handed neo wall. And as we increase the oxygen coverage to 0.22 monolayer, we see the exact opposite. Now the domain wall have switched to right-handed neo wall. In fact, we can take a closer look at this at a different coverage as well. So this chart shows the evolution of the domain wall chirality as we change the oxygen coverage. On this corner, we plot this the histogram of the angle the magnetization makes with respect to the domain wall normal. So this angle clearly illustrates initially we have left-handed neo wall, and eventually as we increase the oxygen coverage, it switched to right-handed neo wall. And in between there's a achiral zero DMI state. And this transition depends on the palladium thickness. This example is corresponding to palladium thickness of 2.76 monolayer. So it is this green curve. If we start out with thicker or thinner palladium, then it requires a different amount of oxygen coverage to switch the chirality. So from this, we can actually construct a phase diagram. So basically, in order to compensate for the palladium thickness change of a 0.37 monolayer, the oxygen coverage needs to change by about a quarter monolayer. And from this, we can extract, induce the DMI by the oxygen coverage, which is about 6.63 millielectron volt per atom for its monolayer coverage of oxygen. And this value is actually quite significant comparing to other transition metal cases, which is illustrated here. And the data points are all determined using this SPLIM technique, so they are self-consistent. The physical mechanism here is the charge transfer because of the difference in electronegativity between oxygen and the nickel. And so this redistribution and rehybridization of the wave function leads to a surface electric dipole moment, and this in turn changes the DMI. And this DMI being quite significant allows us to actually manipulate spin textures. And here is an example, again, of oxygen on this platform. We can see by introducing oxygen, the chiral nature of this bubble domain changes. It starts out from left-handed chiral neo wall and eventually converts to a right-handed skyrmion, going through an achiral state at the intermediate coverage. So this oxygen chemisorption allow us to change the topological character of the skyrmion bubble. So this is the oxygen case. We then went on to study the lightest element, the hydrogen case. So we did a similar experiment using hydrogen chemisorption onto this surface. And oh, I see your question. Why does the domain wall get smaller? So accompanying this chemisorption, there's also a slight anisotropy change, which leads to the modification of the shape. But that effect is not significant to change the topological character of the domain, in contrast to something I will show later, where we focus on the anisotropy change. And please feel free to interrupt me if you have any questions. I cannot quite see the audience, so if you can just speak up, or if I notice something in the chat, I will try to read it. Okay, so for the hydrogen case, we see a similar effect. And again, tuning the system, tuning this multi-layer stack very close to 0 DMI point. Then as we introduce, in this case, less than 1 monolayer, about 0.6 monolayer of a hydrogen, we are able to switch the chirality of this domain wall. Let me see if I can play this video. And you can see the contrast changes from black to white. And this corresponding to the switching of the left-handed neo wall to right-handed. And again, we can quantify the hydrogen-induced DMI. In this case, the induced DMI is much smaller than oxygen. And we know that the difference between the electronegativity of hydrogen and nickel is much smaller comparing to that between oxygen and nickel. And this also shows up in the electron work function change, shows up in the DMI difference. We've collaborated with Stefan Bluger's group who carried out DFT calculations. And this is showing the red curve is without hydrogen, and it crosses 0 DMI for a given palladium thickness. As we introduce a one monolayer of a hydrogen, this effectively is increasing the right-handedness. So we need additional thicker palladium to balance it back to 0 DMI, which is consistent with the experiment. And then this switching is reversible. So here we've done a few cycles. And on the left-hand side, we show the electron work function change. So this monitors the coverage of hydrogen onto the ferromagnetic surface under the UHV environment. And we see this back and forth switching. And correspondingly, we see the contrast along this domain wall changes from left-handed to right-handed. As we introduce hydrogen, it switches. As we turn off hydrogen, we pump it away, it switches back. And then we can repeat this back and forth. And one interesting note is that this effect, particularly as demonstrated by this work function change, is really telling us the effect is being induced by the hydrogen coming into contact with the ferromagnetic surface, the chemisorption effect. It's not hydrogen going into the ferromagnet. So this intrinsically is reversible, which is quite relevant to the use of this effect in solid-state magneto-ionic devices. So this effect intrinsically would be reversible and could be very fast if hydrogen only needs to travel over a very short distance. Now, the previous two examples I discussed, we purposely sit at 0 DMI tipping point. And we, using the chemisorption, we are able to switch to the other side of this tipping point. We see the effect leads to qualitative quadratic switching. This recent study, we shy away from that 0 DMI point. So here we are using 4 monolayer of a palladium. So now we are no longer close to 0 DMI point. So whatever induced DMI by hydrogen chemisorption is going to be pretty small in this case. Instead, we're sitting very close to another tipping point, which is the anisotropy. We change the thickness of the stack so that this layer is very close to spin reorientation transition. And you can see, let me see if I can play this video. As we introduce hydrogen, the magnetization go from perpendicular, so here blue and red correspond to magnetization pointing up or down. As we introduce hydrogen, it goes in plane and the contrast fades. And this, by the way, is the same, we believe it's the same physics as the very nice experiment done by Jeff Beecher's group at MIT, where they shown proton-based magneto-ionics. They were driving hydrogen ion into the buried interface of a cobalt and gallium oxide and toggle the PMA. And here we are able to see this directly and also quantify. It actually doesn't take too much hydrogen to induce this toggling. Now, in this system, as we introduce hydrogen, we not only changed anisotropy to tune it from PMA to in-plane, but we're also able to nucleate what looks like a bubble domain. And upon a close examination, this is not just any bubble domain. This is actually topologically non-trivial. These are magnetic skyrmions. So this is experimentally determined magnetization vector Arrows array plot. And this is actually a new skyrmion with moment pointing up in the middle, pointing down on the exterior, on the outer perimeter, and in between you form this winding configuration. And this is also confirmed by this histogram. And in fact, we see this at many places. This is a chart showing 5 such skyrmions at different regions. The red and the blue, again, representing magnetization pointing down or up. As we introduce hydrogen, so this video will show as we introduce hydrogen, you will see the skyrmions emerge. And then as we pump hydrogen away, they disappear. And this is all done at room temperature, in contrast to conventional cases which require the use of either magnetic field or electric field or electric current. Here we don't have any of that. This is just by introducing a little bit of hydrogen. So we call this pulling magnetic skyrmions out of thin air, or in this case, really just out of thin hydrogen. It is the chemisorption induced anisotropy change, which is effectively like we are applying a magnetic field. We're changing the energy landscape that allow us to nucleate and delete magnetic skyrmions. And most recently, we've done another experiment of changing the palladium capping layer. So in this example, we are still using this nickel cobalt palladium tungsten multilayer stack. We tuned the stack very close to the 0 DMI point. Now we're going back to the 0 DMI point. And we just add a little bit of a palladium capping layer, less than 1 monolayer, in fact, less than a quarter monolayer. We are able to induce, again, a very sensitive transition from left-handed neo domain wall to right-handed neo wall. And we were actually able to observe the evolution of a magnetic skyrmion or skyrmion bubble. Typically, as I mentioned earlier on, so much of the excitement in magnetic skyrmion relies on the topological protection, and which make them very stable and very energy efficient information carriers. Now we are looking at the extreme limit where that topological protection is the weakest, because as we are tuning the palladium capping layer thickness, we are changing the net DMI in the system to go across 0 to let it switch from left-handed to right-handed. And we're looking at where this topological protection is most vulnerable. So here is a series of spleen images at room temperature showing as we increase the palladium coverage, the spin configurations vary. So initially, so if we take a walk along this skyrmion bubble, and indeed, initially, the spins finish a complete 2 pi, and you can see this angle, you walk it along the parameter, it finishes a complete 2 pi, which gives us the skyrmion number 1. And interestingly, at some intermediate palladium coverage, particularly at 0.14 and 0.16, we lose that topological protection. So at 0.14, after wandering around, it goes back to 0. Same thing at 0.14. So at this 2 palladium thickness, we lose the topological protection. Here we just have topologically trivial bubble. And then beyond that, it recovers. It goes back, it switches the chirality, goes to the other side. So by looking at the boundary of this, where this topological protection breaks down, we can actually estimate the corresponding DMI energy difference. The DMI energy difference as we cross this transition point converts to a very small energy cost we have to spend, which is less than 1 attojoule for a micron-sized skyrmion bubble. And this will be even smaller if the skyrmion size itself is smaller. So basically, we're looking at extreme when the topological protection is least stable, how much energy we need to spend to switch the chirality. And this can be decoupled from thermal stability. Same trick as people do in magnetic recording. This latest technology is heat-assisted magnetic recording. You do the writing at elevated temperature where the anisotropy is the smallest, and then you cool it down to room temperature, the thermal stability goes up. So we can apply in principle the same approach. Just when we need to switch the skyrmion chirality, we spend this minimum amount of energy. After we switch it, we can increase the energy barrier to make them stable. So this is the first part of the talk about using this handle to induce DMI and in turn allow us to change spin textures. Before I move on to the next topic, are there any questions? Okay, seems like we don't have questions at the moment. Feel free to ask them towards the end of the talk also. So next example I want to illustrate is using this Magneto ionic handle to influence exchange bias. And we started out doing this for the reason that, as I mentioned earlier, in Magneto ionic systems, the ion migration usually happen underneath some buried surfaces or interface. So it's actually very difficult to directly see the effect. So several years ago, we started out trying to use the interfacial sensitive exchange bias effect, which is between ferromagnet and antiferromagnet. We want to use that to indicate when the interface is changed. What we did back then was to put a gallium iron, which is a ferrimagnet, on top of antiferromagnet nickel cobalt oxide. And the gallium is a strong oxygen getter, so it actually would reduce the interfacial region to magnetic nickel cobalt. And in turn, it leads to very drastic changes in the exchange bias. And we've confirmed the existence of such a ferromagnetic interface layer using, for example, polarized neutron reflectivity. We can pinpoint where this interfacial ferromagnetic layer is. And we can quantitatively determine the thickness, which was about a few nanometers. And then we did a subsequent study to use electric field to drive the oxygen migration. And this was done in a system with 15 nanometer cobalt on top of oxide layer. This is much thicker ferromagnet comparing to some of the earlier experiment I mentioned earlier, cobalt gallium oxide. In the previous study where people switched the PMA, the cobalt was only about 1 nanometer. Here we want to show this magneto ionic handle can go beyond the interface. So we purposely made a very thick 15 nanometer film, and then gave this and use electric field to drive the oxygen from the oxide into the cobalt layer. And this is a polarized neutron reflectivity study. Here, the solid black curve shows the nuclear scattering length density, which corresponds to the structure of the multilayer. The dashed line is the magnetic scattering length density. So here we see the signature from cobalt. Now, when we first applied the electric field to drive oxygen into the 15 nanometer thick cobalt, we see the red curves. So structurally, we see now this curve become more gradual, and this corresponding to oxygen moving into this entire 15 nanometer thickness of the cobalt. And the magnetic signal is reduced to about 30% of the starting state. And this can be reversed. If we reverse the electric field to drive the oxygen out of the cobalt layer, now we see the blue curves. It recovers somewhat the sharpness of the original black curve, but not completely. And the magnetic signature is recovered to about 90% of the original magnetization. So it's mostly reversible, but not 100%. And what we believe is happening here in this case is that initially, as we first use electric field to drive oxygen, the oxygen is going into the cobalt. There is a fast surface diffusion followed by the slower diffusion into the interior of the cobalt grain. And when we reverse the electric field, those near the outer surface would come out first. And in turn, that leads to a screen layer that traps some residual oxygen. And we believe that's the reason that this wasn't 100% reversible. So in this earlier studies, we were mostly using exchange bias, using the electric field effect, try to show the ionic migration. And this gave us an idea that we can actually flip this around. We can use this handle to electrically switch exchange bias. And this is important because exchange bias is at the heart of many spintronic devices, particularly at the bottom, the so-called spin valve, which relies on the pinning by the antiferromagnet to allow people to configure the ferromagnet. And if we can use electric field to switch the exchange bias, this opens up many opportunities to reduce the energy consumption. And in fact, there has been a number of previous studies working on realizing electric switching of exchange bias in multiferroic systems as well as memristors. So this was our recent study following up on the earlier one we did on gadolinium iron nickel cobalt oxide. And this most recent study, we explored gadolinium and nickel cobalt oxide. So here at room temperature, neither one of this component is ferromagnetic. Gadolinium Tc is around 292 Kelvin, and then at room temperature, this oxide, excuse me, is antiferromagnetic. Yet this magneto ionic handle allows us to not only induce a ferromagnetic magnetization, but also allow us to establish exchange bias. So I won't go into great detail, but just point out a few key features. So initially, the S-grown sample already spontaneously have some ferromagnetic signal. And this is because, again, the interfacial region of the nickel cobalt oxide is reduced to nickel cobalt. And then when we do a field cooling procedure, we can establish exchange bias, which is the black curve. And after we apply a voltage gating, the exchange bias is enhanced. It's not a super large, but depending on the system, it can be up to 35% improvement in exchange bias. And we can reset that with a subsequent field cooling procedure. The mechanism, it actually has a lot to do with the microstructure of the multilayers. This is electron microscopy work, scanning tunneling electron microscopy and yields done with my collaborator, Professor Xixiang Zhang's group at KAUST. And we've separately also done polarized neutron reflectivity to look at the interfaces. It's more illustrative to look at the EOS images. And these are the samples prepared under these different conditions, S-grown one, field cooled ones, or field cooled then subsequently voltage biased. And if we look at the EOS image, on the left-hand side is the gadolinium layer, on the right-hand side is the nickel cobalt oxide. In the middle, that's the interface region. And we actually do directly see from EOS, now there is a magnetic nickel cobalt layer, while the oxygen is further below, closer to the oxide layer. So indeed, at the interfacial region, we have this magnetic nickel cobalt layer. And furthermore, there's also evidence of the formation of a gadolinium nickel alloy. So the details here is that this magneto ionic handle actually allow us to change both the effective ferromagnet layer thickness and also the density of the pinned uncompensated antiferromagnet spin. And together, this leads to the enhancement of the exchange bias. And now we are exploring using this angle to try to electrically manipulate exchange bias in magnet tunnel junctions. So far, the studies I've shown that both using the magneto ionic handle to tune DMI spin texture and exchange bias, they actually offer some interesting opportunities in 3D information storage. In fact, there has been a lot of interest in recent years into 3D nanomagnetics. Here are some review articles illustrating the potentials, exploring the complex structure, topology, and frustration in 3D nanomagnetic systems. And this is the very well-known racetrack memory proposed by Stuart Parkin and colleagues. Initially, the first prototype and then the 3D version of such a racetrack memory. And there have also been various proposals of studying 3D nanomagnetics for neuromorphic circuits. And there are also curvature-induced DMI or special types of topological textures because of the geometry. And such kind of a 3D structure also offer potentials for studying artificial spin ice, and then the existence of a large number of magnetic states leads to potentials for complex computation. But in general, there's challenge in studying, not only making, but also characterizing such as 3D structures. And electron holography and X-ray tomography have been utilized to directly visualize the magnetic spin textures. So coming back to what I mentioned earlier, the Magneto ionic handle has a potential advantage in addressing 3D magnetic nanostructures. For example, in the Envision 3D racetrack memory, we have already shown that chemisorption could allow us to switch the domain wall chirality. So that in principle should allow us to manipulate the domain wall propagation direction. For example, under current-driven spin orbit torque, the domain wall would be going in one direction. If we switch the domain wall chirality, it should reverse the propagation direction. And this idea can be adapted into 2D or 3D structures. So that could allow us to address the spin texture in a contactless fashion. So we don't have to put individual electrical leads to each one of this spin texture. We can, using this chemisorption angle, to switch the chirality, for example, very conveniently. And also this can be implemented in solid-state magneto-ionic devices. Even though the chemisorption effects I illustrated earlier was done in ultra-high vacuum for clear control purposes, but the same physics really applies in the solid-state devices. We can imagine using certain stimuli, for example, electric field, to drive the ions in an ionic reservoir, drive that into contact with a ferromagnetic surface and let it do its thing. It can be inducing DMI or anisotropy. It can be manipulating spin textures and so on and so forth. So in that sense, what I illustrated here can be really readily implemented into this solid-state structure. And in that angle, we actually have started to explore some potential prototypes. This is one of our recent attempts at making a 3D interconnected magnetic network. And this was done by a process called nuclear ion tracking. And so we start with a thin polycarbonate membrane, and we expose it in front of a radioactive source. The decay fragments, for example, alpha particle would go penetrate the membrane and create damaged tracks. So instead of a conventional approach of using a single beam, now we can use multiple beams, or say one normal and then additional few beams at symmetric azimuthal angles. So after this nuclear ion tracking process, then we can etch away the damaged tracks, and we use electrochemical deposition to fill up the pores. And this leads us to such interconnected nanowire networks. In fact, this was initiated by an effort early on to try to make materials that are very, very light. So we're able to make nanowire networks with density in the neighborhood of a few tens of milligrams per cubic centimeter. So in the following, I'll illustrate some magnetic networks. And for those studies, we are just using 3 angles. So one normal incidence, and then another one at a 0 and a 180-degree azimuthal angle. So the 3 tracking plane define a 3 tracking angle define a plane, which is illustrated by such white dashed lines. So we have a single tracking plane, and we'll study the effect on their magnetic properties. And this kind of a network is actually quite complex. So in order to study its magnetic response, we use something called a first-order reversal curve. And in essence, this is like a magnetic version of X-ray diffraction. Try to get a fingerprint of the system. Instead of doing a conventional major hysteresis loop, now we do many minor loops. We saturate a sample and then bring it to a particular reversal field. Then we bring the sample back to positive saturation. So this traces out one first order reversal curve. Then we repeat this process at a more negative reversal field. So we end up collecting a family of such forks. And then we take the mixed second order derivative of the magnetization with respect to the reversal field and apply field. And we get this distribution. In essence, this is basically disturbing the system and see the response. If the system is consisting of all identical constituents, let's say magnetic particles that are all identical, then you're just going to get a delta function. If you have a collection that are non-interacting, but they have a finite coercivity distribution, you will have a horizontal ridge in the coercivity versus bias field plane. If there's no coercivity distribution, but they are strongly interacting, you can get a vertical ridge. If you have both of this, they are both interacting and it has a coercivity distribution, you will get this wishbone structure. Experimentally, we see all this kind of features in various material systems. So coming back, we actually listed a number of this capabilities for this fork technique, and we've compiled a little fork library at our group website. So we've used this method, try to capture the magnetic fingerprint of the nanowire networks. I will just point out a few main features without diving too deeply into the details. This is a reference. This is a reference of just parallel nanowires, not intersecting case. And here we see two vertical ridges. This vertical ridge corresponding to demagnetizing dipolar interaction, because adjacent nanowires want to be anti-parallel to the neighbor. So in fact, when you have a collection of such closely spaced nanowires, you end up with this kind of a vertical ridge, as we have seen previously in nickel nanowire arrays. If we change the geometry, when the field is applied along the hard axis, now eventually you see just a reversible component because the field is perpendicular to the wires. In the intersecting nanowire case, we see some difference. So now it's no longer perfectly vertical. In fact, this fork pattern behaves like this wishbone structure. This vertical ridge is tilted, and we can actually learn from the vertical extent of this ridge. The demagnetizing dipolar action is now actually suppressed because of the many intersections we have in the network. And when the field is applied along the hard axis of most of the wires, we actually have a minimum demagnetizing dipolar interaction. So in a nutshell, we actually were able to capture the fingerprints under different geometries. This leads to one potential opportunity that we can, in fact, code information into the magnetic state of such network and then drive it from one portion of the network to another portion. And we've recently carried out magnetoresistance studies. We actually observe pinning by the intersections, and that opens up possibilities to use the domain wall motion to implement multi-state memristors. So finally, I will mention something that's kind of a fun project for us. It's no longer related to magnetism or spintronics. But since we're using the nanowires to make such networks, we actually also made the nanowires into some random metal foams. And turns out they are actually very useful for the current COVID-19 we are facing. In fact, even well before COVID-19, we know air pollution has been a #1 environmental killer. And for air pollution, we worry about ultra small particulates that are below 0.3 micron. They are called long penetrating particles because they can go deep into our respiratory system. And there's some commonality with COVID-19. The the COVID virus itself is very small, about 100 nanometer, but they are usually attached to airborne droplets or aerosols. The larger droplets, they fall off quickly because of gravity. It's the smaller ones that attach to the aerosols with the average size about micron or so. Those are particularly worrisome because they can stay in the air for a long time, especially in enclosed space. And so we wanted to use the metal foam to see if we can develop some effective filtration materials. And this is in light of the challenges of the current filtration media. Turns out this 0.3 micron size range, this is the most challenging to filter. In fact, this is how the references are made. N95 means they are at least 95% efficient at filtering out 0.3 micron particles. And the gold standard is the N95 masks. They use electrostatics. And so that actually makes it very difficult to clean and decontaminate. We know in the earlier days of COVID-19, there were a lot of effort trying to reuse N95. They were really made to be single use. And so you cannot really wash it. Eventually, as you do this, the electrostatics dissipates, and then the efficiency drops to something like 60%. And also, N95 uses polymer-based fibers, and they take a very long time to decompose. So we started out trying to see if we can use the metal nanowire and convert them into foams and use them for filtration. We start out using the same process as we used to make the nanowire network. We grow the nanowire in templates, then we harvest them out. Then we mix nanowires with water and then freeze dry it. And afterwards, we sublimate the ice, and this leads to freestanding metal foams. And we go through additional sintering process to reinforce the structure. So here are some SEM pictures of a variety of different density foams. We are able to make them very light. They are just a small percentage of the bulk density. And we can change the growth conditions so that the morphology evolves, which in turn changes the surface area. And they are very light. So this is an example of a foam, 120 milligram. It can be supported by this green foxtail plant. The same foam is also very strong. So we can put a ton of weight on top of it. It doesn't deform. So this translates to a good comfort and durability if we use it for filtration media. Of course, for filtration, we want it to be very breathable. For example, if you have a plastic bag, that's going to be 100% efficient, but you cannot breathe through it. So we want to make sure the pressure differential is very reasonable. And this plot shows the pressure differential across the metal foam at different air velocity. Just to put into perspective, the pressure differential is quite comparable to N95 mask. And here, the smaller the number, the better. And so in some of our samples, this breathability is even twice as good as N95 mask. And then the efficiency is also very good. Without using electrostatics, just using the microstructure of the foam itself, we were able to achieve above 95% efficiency for this 0.1 to 1.6 micron size range, which is particularly relevant for COVID-19. And another advantage is the foams are reusable. So here is an example. We used the two foams to filter out smoke particles. And after we do the filtering, we can just wash it and we can reuse it. So it's this combination of the efficiency, robustness, reusability makes such foams very attractive. Furthermore, they actually open up additional angles that we can potentially clean the air we're trying to filter, not only just filter out particles, but we can neutralize toxic or unwanted gases. So in fact, last year we entered into this BARDA Mask Innovation Challenge, proposing using our metal foam as the filtration media. We were selected initially as one of the 10 phase 1 winners. And then earlier this year, we were also selected again as one of the 10 phase 2 finalists. So it has been a fun project for us, which we are continuing. Okay, so at the end of the talk, hopefully I've illustrated a number of functionalities that we could achieve using the Magneto ionic handle. Particularly, I talked about using this effect to induce and change DMI and anisotropy, and in turn use that to manipulate spin textures. And this opens up other functionalities such as electrical control of exchange bias, and then implement some of these functionalities into 3D networks for potential 3D information storage. Then finally, I touched upon this foam project. These are the people who really did the work. A number of the people currently at Georgetown, Dr. Gong Chen, who led our effort on the chemisorption studies, Alberto Quintana, Tridaman Bhattacharya, graduate student James Malloy, Chris Jensen, Hugh Chen, Willie Beeson, and RE student Abby Firm. And my former student at UC Davis, Dustin Gilbert, Nat Burks, Peter Mary, and Matt Robertson, my colleague Gen Ying at Georgetown, and then my wonderful collaborators all over the world, particularly Andrea Schmidt's group at LBL, Alex Gruter, Julie Borchers and colleagues at NIST, Xishan Zhang's group at Chaos for Imaging, Roland Wiesendonger's group at Hamburg, Stefan Bruger's group at Jülich for DFT, and other colleagues at Complutense, Autonomous University of Madrid, Kwanki University, Nanjing, and Fudan University. So with that, I'll stop here. Thank you very much for your attention. I'll be happy to answer questions.
Okay, thank you very much for your talk. It was very interesting. Let's see, for the audience, the way that you ask questions is to, the way the software works is to type it into the Q&A or the chat, and then we can read the questions, and then we'll go ahead and answer them. Maybe I can start out with one. I mean,
please.
The idea of making a new memory of some type to go in with electronics in some future vision of, cross-material integration of chips. Could you talk about how that would work with the skyrmions here and switching them and all of that?
Yes, that's a great question. So there has been a lot of interest in using skyrmions or chiral domain walls because of their topological protection. So the hope is they can be the information carrier in a much more energy efficient way comparing to conventional means. So one of the envisioned platform is this racetrack memory. So information will be stored in either magnetic skyrmions or chiral domain walls. And then as it passes through a readout point, it will correspond to 0 or 1. And so right now there are a number of challenges. One is how much of the envisioned benefit can really be realized. One limiting factor is in real system, there's always defects and pinging. So the energy efficiency so far has been shown mostly when you don't have to move the spin textures very fast. If you move it at high speed, and then the spinning effect starts to show up. So that has been one bottleneck. People have come up with various ways to try to address them. For us, one unique angle is we are able to use the chemisorption angle to manipulate such spin textures, either skyrmions or chiral domain walls. And we can, for example, imagine using a magneto ionic gate to pin a domain wall, so it will be stuck somewhere. Then that can be integrated with some learning process and implemented potentially in some neuromorphic circuits. We're really trying to do something that no other ways can achieve, in the sense that we are trying to transform the structure into something else because we are able to change the interface. So that aspect is rather unique, which we call it reconfigurable. So we are hoping to do some device prototype demonstration to show that we can really implement this magneto ionic functionality into some device that right now there's no precedent.
Yeah. Okay, thank you. A couple of questions, Tommy Tai, for the FORC results you've shown. Could you re-explain why you presented the data in the HC-H underlying C basis instead of the standard HRH basis? Are there presentations?
Yeah, oh, great. Yeah, sharp eyes. I went over there very quickly. So fork distribution can be plotted in either one. Okay, so I didn't really talk about this histogram idea. So one way to get a physical sense of what fork is trying to do is if we envision the system is consisting of many elemental hysteresis called hysterons, which has unit magnetization 1. And then you just need a switch down field and a switch up field to characterize. So the way we're doing the fork measurement, for example, bring the field to a particular reversal field. Imagine now we have switched down a set of the hysterons that have a switch down field in this range. Now, as we measure back up, we are switching back a subset of the previous hysteron that have already reversed. So in essence, we just need a switch down, switch up field to characterize. And we can define local coercivity, which is half width of this hysteron, and the bias field, which is the shift of this hysteron from origin. So this bias field represents the interactions. If there's no interaction, then this will always be centered. So when we plot the fork distribution, we can use either coordinates. We can use HCHB, which illustrate distributions of a coercivity and the bias field. We can also use HHR, which is H is the applied field, HR is the reversal field. They tell us different aspects. So for example, when we are trying to illustrate distributions, it's easier to see it here in coercivity and a bias field. But in some other cases, when we try to probe, particularly, for example, in this figure from this paper, we're trying to see where we have irreversible switching. It's actually easier to see it in applied field and reversal field coordinate. In a nutshell, fork gets rid of reversible switching. So any feature you see in the fork diagram corresponds to some irreversible switching. So when we plot in this coordinate, we can immediately tell, okay, this is where I begin to have irreversible switching. Before this reversal field, so for example, 1 is here. Before that, there's nothing irreversible about it. So I get 0 feature. And between 1 and 2, I get this pattern. This corresponds to something happening in one of the stacks, so on and so forth. So we can choose either coordinate depending on what feature we try to highlight. That's the gist of it. And in this mini fork library, we've shown many, many examples of different systems with all these different aspects.
Yeah. Okay, great. Thanks. One last question. Is skyrmion a quantum object ? How to understand the quantum in skyrmions ?
That's a great question. I believe it is, and it involves the spin and the topological nature of the skyrmions has to invoke quantum mechanics. That's the short answer of it. In practice, as I mentioned earlier, much of the envisioned benefit still hinders some practical issues such as pinning. That remains to be resolved. And also our most recent study looking at when the topological protection is the weakest, hopefully will address some practical aspect of it. But I believe intrinsically, yes, skyrmion is quantum.
Okay, well, thank you very much for giving the talk.
Thank you.
Great.
Thanks for all the questions.
Okay, great. Thanks.